So hello everyone and welcome to the YEA F equals MA lecture series. Today's lecture will be on momentum. Okay, so an introduction. What is momentum? Well, we define the momentum of a mass to be equal to the product of its mass and velocity. So P equals mv. And this is a vector because when you get a scalar like m and then you multiply by a vector like v, you'll get a vector. So like an object's here has some mass. This is its velocity. Its momentum will just be a vector in the same direction, just magnitude multiplied by m. And it's also useful when we're defining force because actually Newton's second law, originally it stated that the force equals the derivative of the momentum. Oh. And the F equals ma that a lot of people know, that happens in the special case where the mass is constant, because if the mass is constant, then we can just take it out here times dv dt, and then this will give us ma. So this is kind of where F equals ma comes from, but the original equation was F equals dp dt. All right, so let's do some examples. And this is a nice conceptual example. I'll give you a few minutes and I'll actually launch a poll this time. So see, and yeah, if you have any questions, you can ask me or just submit your answers. I guess this time it's a poll. Okay, it's been a few minutes, so let's talk about this. So, what's going on here? So we have a ping pong ball and a bowling ball. Oop, what happened? Okay. So we have our two balls. Let's call like the mass of the ping pong ball mp, and the mass of the bowling ball mb. And yeah, okay. Uh Technically I guess I didn't specify whether it could be 0, but yeah. Okay, assuming it's not 0, which I probably should have said, but what would happen then? So we know that they have the same momentum. So the ping pong ball, let's say it's moving with a velocity Vp, oh, and the bowling ball will be moving with a velocity of Vb. Okay, so they have the same momentum, which means that mp times vp is equal to mv, mb, mb times vb. Okay, but now we want to compare their kinetic energies. So from last time, you would uh you would use 1/2 mv squared for your kinetic energy. Um okay, I guess we're going to assume that the ping pong ball is less massive than the bowling ball. Um, yeah, it would be very hard to make something, I guess not that hard, but it would have to be a very dense ping pong ball if it's heavier than a bowling ball. But anyways, so now we're comparing 1/2 mp times vp squared versus the 1/2 mb times vb squared. What if momentum is relativistic? I actually don't think that changes the answer because has a higher v, it also has a higher gamma. But anyways, assuming these are normal ping pong balls and normal bowling balls. So if we're comparing these, well, we can actually just, I guess one way of doing this is dividing by 1/2 mpvp, and then this one we divide by 1/2 mbvb. Since these are the same, we can just compare the quotients, which will be vp and vb. Okay, but if the ping pong ball is less massive than the bowling ball, that means that the ping pong ball must have a greater velocity. So in effect, this basically means that the ping pong ball will have the higher kinetic energy. Um, rest energy is not counted in kinetic energy normally. I'm not sure. Yeah, okay. Mm, oh, I see what you mean. Yeah, assume they're regular ping pong balls and regular bowling balls that are non-relativistic. All right. Let's just go on and talk about impulse. So, what is impulse? Well, impulse is, we define it as the integral of force with respect to time. And what this gives us is, if you remember from earlier, well, force is just dp dt, right? So what we'll get if we move the dt to the other side. So dp is force times dt. Oops, no integral on, no vector on here. Okay, so we'll get that integral dp equals to the integral of the force with respect to time. So if you integrate this, what this basically tells you is that the impulse is the change in momentum. So yeah, as I wrote down there, delta p is equal to the integral of force dt. And I guess this, for in terms of F equals ma, this is just useful if they give you a graph of like force, or this would be time, and then there's force here. And then they give you some graph and then ask you what's the change in momentum. Well, it's just the area under the graph. All right, cool. Another example. This is actually an F equals ma problem, I think. I will open up another poll and give you a few more minutes to think about this one. All right, it's been a while, so let's talk about this question. Um, okay, I realize I haven't really talked about conservation of momentum yet, but ooh, for this problem, what you need to know is that I guess you need to know conservation of momentum, but so the idea here is that the what happens is we have an astronaut over here, okay, and it it applies a force on the bowling ball, okay, and so the bowling ball gets launched away. But by Newton's third law, the bowling ball will also have to apply a force on the astronaut. So the astronaut gets launched that way. And what happens? Well, we don't know how much time the force took, but we do know that whatever force that the astronaut applied on the bowling ball, the bowling ball also applied the same force on the astronaut. So what happens when we look at the impulse? Well, we get integral force d time. And we see that since the force is the same for both the bowling ball and the astronaut, the impulse, or I guess the magnitude of the impulses on both of the objects were the same. So what does this mean? This means that basically they have the same momentum, just in the opposite directions. Okay, so let's call the astronaut. Let's say the astronaut has mass m1, and then the astronaut gets launched at v1 that way. And then there's a bowling ball, has mass m2, and it gets launched v2 that way. What equations do we have? Well, we just argued that we should have the same momentum m1 v1 equals m2 v2. And we also know that their relative speed is 50 meters per second. So what this means is that m1, not m1, v1 plus v2 equals v, where v is their relative speed, in this case 50 meters per second. All right, so we have a system of equations here. We have two unknowns, which are v1 and v2, and we have two equations. So we can solve this system of equations. The way I solved it is just multiply both sides by m1 v1 plus m1 v2 equals m1 v. And then after that, substitute in like m2 v2 plus 1 v2 equals m1 v. And then from here, we can solve for v2. It's equal to m1 v over m2 plus m1. And then after we do that, well, what's the question asking us? It's basically asking us for the impulse delivered to the astronaut, which is the same as the final momentum of the astronaut. So this should be equal to m2 v2, which is m1 m2 v over m1 plus m2. And if you plug in the numbers given, you will get approximately 455 newtons per second. Newton times seconds, sorry. Newton seconds. So that's our answer. Very cool. All right. Now let's talk about conservation of momentum, which is basically what we tried to derive in the previous example. So if we consider an isolated system, is basically a system that doesn't interact with its surroundings. So there's no external forces, so nothing outside of the system can apply a force on anything inside the system. That's basically what it means. And if we have two objects like we had in the previous problem, we have Newton's third law, which says that they must exert equal and opposite forces. So we get that the derivative, or I guess the force on A, which is the same as the negative of the force on B, is the derivative of the momentum of A, but it's also equal to the negative of the derivative of the momentum of B. So then when you add up the momentum of A and the momentum of B, and then you take the derivative, you get 0. And what this means is that the total momentum PA plus PB is a constant. This is because if its derivative is 0, it cannot change. So this is what we call conservation of momentum. Basically, it's the momentum of a closed system doesn't change. And we can use this to solve problems involving collisions, which is our next topic. Let's first do an example here. I will start another poll. Very cool. Yeah, I'll give you a few minutes for this one as well. Okay, cool. It's been a while. And so let's do this problem. Also, just curious, do you want me to share the results of the poll or not share the results of the poll? Yes. Okay. Some people are saying yes. So I guess from now on, I will share the results. And for this one, it looks like everyone chose B, which is good because B is like kind of correct. Okay, so what's going on here? Well, we have one particle, and initially it has like, it's just sitting there. It has no momentum. Okay. And then it explodes. Let's put this up here. So what happens when it explodes? We know that two particles come out at right angles to each other, and each of them have an equal speed of v. All right. But what? So the initial momentum of the whole system is zero. And by conservation of momentum, this means that the final momentum also has to be zero. So since they're all equal masses, I guess the velocities of all of the final particles have to add up to zero. So we have one particle with momentum mv, and then we also have a particle with momentum mv. Well, why is the speed of the third particle root 2v? Well, this is because remember that momentum is a vector, right? So we have to do the vector addition of the three velocities. So the momentum of the third particle should be this right here, which would be the negative of the sum of these two momentums. So by Pythagoras theorem, it will be b squared plus v squared root 2v. All right. That was pretty straightforward. Now let's move on to collisions. So yeah, whenever two particles collide, I guess a particle exploding in some cases, like you might be able to consider that like a collision as well. Oop, did I do? And basically just when we have a collision, we have to have momentum conserved. But what about energy? So is energy conserved? Well, oop. Technically energy is always conserved, but what we consider here is kinetic energy. So there are two types. If kinetic energy is completely conserved, then it will be a perfectly elastic collision. And if kinetic energy is not conserved, then it will be an inelastic collision. And most of the time in this case, that basically means that energy is lost to like heat or sound or any other form of energy that's like not kinetic energy. And I guess so inelastic collisions broadly is just when the energy decreases. And a completely inelastic collision is actually when the two objects stick together. So before they're like going in opposite directions, right? But afterwards, they just stick together and then they're now just one big blob and they're going that way. And why is this called completely elastic? Well, this is because I think this is actually it's the situation where the most kinetic energy is lost. And just a side note, like in the case of our collision, not our collision, the previous problem where the particle explodes, that's actually a gain in kinetic energy. You normally won't see that, but some people consider that to be what they call a super elastic collision, where basically there's some potential energy in the particles, and then when they collide, the potential energy is released. So it will increase the total kinetic energy. All right, now we can do our fourth problem. Let's open up another poll and launch. So I'll give you a few minutes for this one as well. Okay, cool. So we have some responses. Let's start talking about this problem. Okay, so what we have, first let me end the poll and share the results. So a lot of you picked E, which is the answer in this case. What we have here is a child sliding across a frozen lake, so no friction here, which means that there aren't any external forces, so we can apply conservation of momentum. So we have a child here, and he's sliding at a velocity vc. And then there's another child who's 3 times the mass of the first one. So let's just put variables here. The first one, if the first one's mass m, then the second child has mass 3m. Okay, so now let's use conservation of momentum here. First of all, what type of collision is this? Yeah, so the two children, they hold on, so they're both moving together. So what this means is that this is a completely inelastic collision. Okay. So, oops, it appears that my text. Okay, there we go. So we have a complete inelastic collision. And so we can use conservation of momentum here. So what's the momentum initially? Well, it's just the small child has momentum m times vc, and the large child is at rest, so 0 momentum. So this is just our initial momentum. Now, what about after the collision? Well, the momentum has to stay the same. This is still a momentum. But what happens after the collision is we have the small child here and the large child here, and they move as one unit. So we can consider them to be one like blob that's moving at a mass v final, that's moving v final. And the total mass of this system will be 4m. Okay, so we have that m times vc is 4m times v final, because this is the final momentum. So then we can just get that v final is vc over 4. Cool. And uh-oh, I actually added another problem. So let's reload this. What? Anyways, where's my problem? That is weird. Okay, let's do this problem first, and then I will recompile with my added problem. All right. So we have two important problems, I guess, here, which are just the formulas for elastic or inelastic collisions. So I will give you a few minutes to work on these, and these aren't multiple choice, so please send me your answers in chat. And as always, if you have any questions, feel free to also ask me. Wait, hold up. Can you see my slides right now or no? Okay, that is a slight problem. Yeah, okay. Um, that is very weird. Okay. What happens? Let me just try restarting my screen and all right. Now can you see the slides? All right, cool. So let's first talk about the first problem. So we have two blocks, M1 and M2 here. And M1's initially traveling V1 and M2's initially traveling at velocity V2. And they collide completely inelastically. So what this means is that they have to stick together. And we want to find their final velocity. So let's go over here and see what's going on. Okay, oops, that's a bit too much. So this is similar to the previous problem that we did. So what we first want to do is find the initial velocity, the initial momentum. So what is the initial momentum? Well, the first block has momentum m1v1, and the second block has momentum m2v2. So when we add them up, this is our initial total momentum. Now, what is our final momentum? Well, after they collide, they're going to basically form this big block with mass m1 plus m2. And they're going to be moving at the same velocity v. So what is their final momentum going to be? It will just be m1 plus m2 times v. Okay, but by conservation of momentum, what happens? We get that m1v1 plus m2v2 has to equal m1 plus m2 times v. So this just means that v equals m1 v1 plus m2 v2 divided by m1 plus m2. So this would be a formula for inelastic collisions. Okay. Now let's go back to our slides for a moment and work on question 2. So we have two blocks, mass m1 and m2, and now they collide completely elastically. So this is slightly different, and it's also slightly harder. So we want to find what their final velocities are. I'll give you another few minutes, see if you can try to solve this problem. Okay, it's been a while. I should probably I'll first give some ideas on how to solve it. So we know last time when we had an inelastic collision, this is what happened, right? We have we used conservation of momentum and we found that it was really easy because um after the collision, both of the blocks had to move together as one single block. So there was only one final velocity. But when we go to our second problem, the elastic collision, this is slightly harder because now what we still have our two blocks here. Um, our two blocks here, copy and paste. Paste. Oop. Uh, let's just redraw it. So we have M1 here moving with velocity V1, and then we have M2 here moving with velocity V2. But what we have after the collision is going to be slightly different. So after the collision, we might have both of the balls bouncing away. So maybe this one's moving at some velocity, let's call it V2 prime. And then this one's also moving at some velocity, it might even be negative. Let's call this V1 prime. So we have two unknowns here. So we need two equations. So we have the conservation of momentum equation. It will be very similar to last time. M1 V1 plus M2 V2 is equal to M1 V1 prime plus M2 times V2 prime. But we need another equation. So what is this equation? Well, we know that it's a perfectly elastic collision, right? And if we go back some, yeah, it will be conservation of kinetic energy. So what is the initial kinetic energy? 1/2 m1 v1 squared plus 1/2 m2 v2 squared. This will be equal to half m1 v1 prime squared plus half m2 v2 prime squared. All right, now we have two equations and two unknowns, so we can solve it. And since it's 2:30, it will be time for our break. I'll give you guys a 5-minute break, and I guess you can continue to work on this problem or take your break and then continue to work on the problem, whatever you want. I'll be back at 2:35. I mean 2:37 because we started at 32. Um, yes, that is a smart way of doing it. All right, I am back. And let's continue working on this problem. Um, Basically all we need now is to solve this system of two equations. All right. Um, let's start talking about it. So, first of all, we know how to do this. We know that one solution is V1 prime is equal to V1 and V2 prime equals V2. So we can just remember this as we work. This could make our solution much easier later on. So I guess we just have to try and eliminate stuff. So what can we try here? We can try eliminating V1 prime. It's equal to M1 V1 plus M2 V2 minus M2 V2 prime over M1. And all right, what happens when we try substituting this in? This is going to be pretty long, but let's just do it. So first of all, from our conservation of energy equation, let's get rid of all the 1/2s and then plug in our expression for V1 prime. All right, almost there. Okay, so then we're going to get this big equation. But like Chris said, we can try jump straight to the roots by using vietas. So this thing becomes very helpful because we know that V2 prime equals V2 should be a solution of this equation. But this equation only has two solutions. So what's the other equation? I mean, what's the other solution? Well, we can find first what the sum of the solutions is by VA does. And then hopefully this will just subtract this solution to get the other solution. All right. So let's do that. When we expand this, let's try expanding this first of all. It should be equal to m1v1 plus m2v2 minus m2v2 prime all squared over m1. And this should be equal to m2v2 prime squared over m1. And then we'll also have minus m1v1 plus m2v2 times 2 times m2 over m1. And then plus a lot of stuff. We don't really care what this stuff is, because we want the coefficients of v2 prime squared and v2 prime. And all of this stuff shouldn't have a factor of v2 prime. Okay. Now, moving on, what will the coefficient of v2 prime squared be? It will just be m2 squared over m1 plus m2. And then we'll have the minus 2 m2 times m1 v1 plus m2 v2 over m1 times v2 prime. Oops. Okay. Now what do we do? We'll get that our two solutions. One of them will be v2. And the other one is the v2 prime that we actually want. This will be negative b over a by Vieta's formulas. So what this will be 2m2 times m1 v1 m2 v2 over m1 divided by m2 squared over m1 plus m2. All right, this is a bit messy. And we can do some quick maths to simplify. M1 v1 plus m2 v2 divided by, we would have something like m1 plus m2. All right. So then what we should get is that v2 prime is 2 times m1 v1 plus m2 v2 equal minus v2. This will give 2m1 v1 plus m2 v2 minus m1 v2 divided by m1 plus m2. Interesting. All right, this was quite tedious, honestly, but there is a better way to do it, which I will show later on. But first, let's go back to our slides. Let's go back to our slides and do some more practice problems. All right. Example, this is also an F equals MA problem. I think it's quite instructive. And so I will open up another poll. Yeah. And I'll give you a few minutes for this problem. As always, if you have any questions, don't hesitate to ask me. Okay, this is a bit of a tough question, but let me start going over it. So I'll end the poll soon and share the results. So I guess 2 people picked A, which is nice because A is the correct answer. And how do we get this? What's going on in this question? Well, let's take a look. So I always start with a diagram. We have a 0.6 kilogram, 65 kilogram ball. It's not important. Let's just call it, let's just say it has mass M1. Okay. This ball has mass M1 and it is moving 5 meters per second. Let's call that V0. And it collides with another ball, has mass 0.75. Let's call that M2. And the other ball is initially at rest. Okay. And after the collision, the M2 ball, it moves off with a velocity of 4 meters per second, but we don't know what the direction is. And we know V2. So now the question's asking us, if we know that, or we also know that V1 went in a perpendicular direction. So what would that look like? Basically perpendicular to this, I guess. This would be V1. We just want to find V1. All right. So let's take a look at this. Remember, for collisions, our 2 big formulas will be conservation of momentum and conservation. I guess in this case, we won't have conservation of energy because we don't know whether or not it's an elastic collision. The problem never told us. But nevertheless, we can still solve this. So let's think about it. Initially, we're going to have, what's our initial momentum? Well, initially we just have M1. It's moving with velocity V0, and M2 is at rest. So our initial momentum is M1 times V0. That's cool, but now what's our final momentum? So let this be the initial direction of V0. We're going to have V1 and V2 going off at right angles. How to draw this? Let's draw like that. Oops. No. Okay, so we'll have V1 and V2 at right angles. But we don't know the angle. So let's call this theta. And that means that this will have to be 90 minus theta. So what this means is that this is also theta. Okay, but remember that momentum is a vector, right? And if we want a vector to equal another vector, its components have to be equal to the other vector's components. So initially, we have m1v0 this way, and nothing in the y component. There's nothing here. So when we add up these two momentums, we should also have no y component. This means that the y components have to cancel out. So the y component of the first one is going to be m1 v1 times the sine of theta, right? And this has to be equal to the y component of the second momentum, which is m2 v2 times cosine theta. All right. But their x components also have to add up to the initial momentum. So we get another equation, which is m1 v1 times cosine theta plus m2 v2 times sine theta equals m1 times v0. All right. So now let's think. We know what m1 is, we know what m2 is, and we know what v2 is. All we have to do is find v1. And we don't know what theta is either. So we have two unknowns and two equations. Technically, we could solve this system of equations. Now, this seems like a tough system to solve, right? Now, it is solvable, but there is a faster way to do this problem. And I will show you right here. So let's just stop thinking about components for a second and think about the overall vectors. So we know what this vector is. This is going to be our m2 v2. We don't know what this is. This is the momentum m1 v1 of the first ball. But we know that they have to add up to m1 v0. And we know that they're 90 degrees from each other. Well, we can just move this vector over here, and this will make a right triangle. So now this gives us an easy way to solve for v1. All we need to do is use Pythagorean theorem. M1 v0 squared equals m2 v2 squared plus m1 v1 squared. And we will very quickly get that v1 is equal to square root m1 v0 squared minus m2 squared v2 squared over m1 squared. And if you plug in the numbers, this is around 1.92 meters per second. And so our answer would be A. All right. Now, let's do another example. And I will restart our poll. Let's try doing this problem now. Okay, it's been a while now, and in the interest of time, I will just end the poll very shortly and share the results. Okay, um, this must have been, so the answer here is actually E. It's nice one person chose it. Um, why is this? Well, this question, I think you probably just have to go through each choice and see what happens if that choice were the case. Okay, so the first choice is the two balls are both moving directly east. Um, yeah, basically, let's just see what's going on. So we have a 3 kilogram ball moving here, and mm, it's moving at 10 meters per second. So the this ball will have momentum 30 kilograms meters per second. And then there's also the 2 kilogram ball moving west at 15 meters per second, which also has momentum 30 kilograms meters per second. All right. So, oh, you probably can't see that. Let's move it over. What will happen if both of the balls are moving directly east? Well, if they're both moving directly east, then what will happen is that there will be a net momentum to the east, and that can't happen because initially the two momentums canceled out, right? There was 30 kilogram meters per second this way and 30 that way. So the total is 0. So we need a total momentum to be 0. Oop, keep on trying. Let's switch to this. Okay. So A is not possible. What about B? The 3 kilogram ball moves directly west at 15 meters per second. Well, what happens here if the 3 kilogram ball moves directly west at 15 meters per second? Then in order for the total momentum to be 0, the 2 kilogram ball has to move directly east, and it has to have a speed of 45 halves meters per second. Okay, but why is this a problem? Well, is kinetic energy conserved here? And actually, the answer is no, it's not. In this collision, kinetic energy actually increased because if you think about it, um, the 3 kilogram ball, it went from 10 to 15 meters per second, right? So that's an increase of speed. That's also an increase of kinetic energy. And same thing with the 2 kilogram ball. It went from 15 to 45 halves, which is 22.5 kilogram meters per second. So that would also be an increase in energy. So there's a net increase in energy in this case. All right. What about answer choice C? Draw here. All right, that says the 2 kilogram ball moves directly north at 10 meters per second. Okay. Well, for the 3 kilogram ball to balance out the total momentum, it has to move 20 thirds meters per second directly south. Now, is kinetic energy the same? No, it's not, because the velocity of the 2 kilogram ball decreased, but the velocity of the 3 kilogram ball also decreased. So that cannot be the correct answer. So B is out, C is out. What about D? The 3 kilogram ball is at rest. Well, if the 3 kilogram ball is at rest, in order for momentum to be conserved, the 2 kilogram ball must also be at rest. But this has 0 kinetic energy, so clearly we lost some kinetic energy in this collision. And now, so this can't be the case. And now choice E is the only choice left, and it's the right answer. And what happens here is that the 2 kilogram ball 15 meters per second south, and the 3 kilogram ball is 10 meters per second north. So notice that they're both moving at the same speed that they were before. So this means that they have the same kinetic energy, and so kinetic energy is conserved. And this is why this is the only choice that is correct. Okay, let's move on. Let's talk about center of mass. Ooh, did I make a section for this? I don't know. So the center of mass is kind of useful because you'll see why later, actually. So let's first define it. It's like the weighted average of the positions of all of our particles. So if we have, let's say, particle here is 1 kilogram, and a particle here is 2 kilograms, where's the center of mass? Well, it would be along this line, first of all, and it would be right here at 2/3 the distance between these two. And the reason why this is, well, we can plug it into our equation. If we call this 0 and this position 1, it will just be 1 kilogram times 0 plus 2 kilograms times 1 over 1 kilogram plus 2 kilograms. This is 2/3. Or we can just think of it like a weighted average. So this mass is twice as massive, so it can pull on the center of mass twice as much. So the center of mass should be twice as close to this one as it is to this mass. And in general, it's just the formulas up there. You just take the sum of mixi and then divide by the sum of the masses to get the center of mass. And we can also define a center of mass velocity, which is the same thing but with velocities. And this is the formula here. It's quite similar. And you can notice that this is actually the center of mass velocity. We can actually just write this as the total momentum divided by the total mass. So we also have P equals mv for the total, the center of mass system as well. All right. Now, why do we want to do this. Um, so one way of thinking about this, since momentum is conserved, right? We get that momentum is conserved. If we assume that mass is conserved, which it is basically always conserved, yeah, if we're not talking about like relativity or anything, and we have a closed system, so most likely mass is conserved. What this means is that our center of mass velocity is constant because it's just the quotient of the total momentum and the total mass. But if these two are both constant, then the center of mass velocity is also constant. So with that in mind, let's do our example problem. And this is from the F equals MA exam. I posted a screenshot because it would be tough to do all the images. And yeah, so it's a bit small, but hopefully you can still read it. And I will relaunch my poll. Oh, okay. Actually, for this question, we would need to also know about angular momentum. So what to do? What I'm gonna tell you right now is just it's not C and it's not D because of conservation of angular momentum. So let's eliminate these two. And for the few people that have already answered, I will end the poll and then restart it. So let's relaunch it. Okay, yeah, C and D are not correct because of conservation of angular momentum, which is violated in those cases. And also, in the interest of time, I will end the poll like very, very soon. All right. I did prepare, let me think. I prepared 2 more questions after this. Um, I will just end the poll right now and share the results. All right. A lot of you chose E, which is nice because E is the correct answer. So what's going on here? Well, first of all, we know that the system evolves through internal forces only. So this means that momentum has to be conserved. Well, if we look at answer choice B, we can see that momentum is not conserved here because there's a net momentum of 2 kilograms meters per second that way, which is not allowed because initially the total momentum is 0. So the total momentum after some time also has to be 0. Now, what about A and E? Well, what I was just talking about is the center of mass velocity. So the center of mass velocity in this case also has to be 0. And what this means is that the center of mass can never move. So initially we see that the center of mass is around here. So if I can, it's around here. Oop, what happened? Yeah, the center of mass, that was bad. It's at position, I guess 1,0, if we treat this as like a coordinate plane. Okay. But after some time in answer choice A, what's its center of mass? Well, the center of mass becomes 0, 0, and this is not allowed. So we can also eliminate choice A, and the only choice we're left with is answer choice E. Very okay. Let us go on to the next example. And I will relaunch the poll. By the way, this is also an F equals MA problem. Yes, that's why the 21. Okay, it is time, so I will very quickly go over this question. I'm going to end the poll right now. And yes, the answer is A. And the reason is because, so what we have here is just two balls connected with a stick, right? This has mass 3m, this has mass m. All right, and the center of mass going to be around here, right? And the key thing to notice here is that, okay, there's going to be gravity in the vertical direction, but there aren't any forces in the horizontal direction. So what this means is that we're going to have the center of mass. It can accelerate in the vertical direction, but it can't accelerate in the horizontal direction. So after it falls down, the center of mass will be where, I guess, right below where it was before. And so initially the second ball was here, now it moved here. And since this is 3 times the mass of this one, this will be L over 4, and this will be 3L over 4. So this is our answer. Wait, is it? Let me double check that. Uh, is that what it says? Ooh. That may be a typo in the F equals, because this is a past F equals MA exam. I guess, no, that's weird. Anyways, let's just assume the top ball was 3M and the bottom ball was M. Wait, where am I? Okay. And this is my final question. It is also a modified F equals MA problem. But since we're out of time, I'm going to skip this question. You can read it later on in the recording if you want to. And I will end the lecture there. Oh, that wasn't my last question. Okay, let's talk briefly about the center of mass reference frame. So collisions, oh, this is the easier approach I promised earlier, which is, if we look in terms of the center of mass, what happens for an elastic collision is basically what can happen for a head-on elastic collision is after the collision, the directions of the velocities just reverse and they're the same magnitude. So this is kind of what we saw earlier with our perfectly elastic collision derivation. If we go all the way up here, this is similar to the formula we saw. And so this is one nice way of explaining it, because if we just look at this setup, we can see that momentum and kinetic energy are conserved. All right. And derive this by working in the center of mass frame. This is kind of what we saw earlier when we got that the like the sum of the two roots ends up to be something very nice in terms of the center of mass velocity. But anyways, other than that, if you want to work on the examples that I didn't get to today, you can watch the recording and read those examples. Otherwise, there are some optional extra practice problems. And that is it for my lecture. And I will see you in the next one.